In this video, we're going to take a look at aldehydes and ketones. What I've drawn here are some generic representations of an aldehyde versus a ketone. And in looking at both of these, you'll notice that they both contain a C double bond O functional group. In general, we can call any functional group that has a C double bond O, the actual C double bond O component is often referred to as a carbonyl. C-A-R-B-O-N-Y-L. But these two particular carbonyls, the aldehyde has one alkyl substituent, which we're indicating with an R, and a hydrogen. In a ketone, this carbonyl group has two alkyl groups, and they could be the same or different alkyl groups, just basically two different or two carbon-based substituents coming off of them. So one other thing I'll mention, aldehydes are often abbreviated as RCHO. This is an abbreviation of the aldehyde. So you'll often see that written out. So if you ever see that in a problem or an exam or anything like that, whenever you see CHO, that's just a simple, simplistic way to abbreviate an aldehyde. So what exactly are carbonyls, and what's going on with the structure of these? So if we were to sort of zoom in on the structure of a carbonyl, like an aldehyde or ketone, and look at the structure of the actual bonds that are occurring in these. So we have our carbon, and I'm just going to draw this with two different R groups, R and R prime. So it could be a ketone. So like we saw in carbon-carbon double bonds, in the carbon-oxygen double bond, we actually have two different types of bonds going on. So here we have what's called a sigma bond, okay, which is the direct head-to-head overlap of two electrons forming now a covalent bond in this head-to-head overlapped bond called a sigma bond. Now the oxygen is going to have two what are called lone pair electrons that are not going to be bonded to anything. So we're just going to kind of draw those out here. And then lastly, the double bond part is going to come about because of the existence of one of these pi bonds. So just like we saw with the carbon-carbon double bond, a carbon-oxygen double bond has both a sigma bond and one of these pi bonds. Now, let's also, while we have this figure up here, let's talk about the fact that these are polar groups. There's an asymmetric distribution of electrons here. The oxygen is much more electronegative than carbon. So this end of the molecule is partial negative. Okay, we have these negative electrons here, plus the oxygen is pulling electron density away from the carbon, and therefore the carbon would be delta plus. So we can now draw a polarity arrow that would look like this, where we now point the polarity arrow towards the negatively charged part of the carbonyl, and we have this little crosshash, which looks kind of like a positive charge residing over the carbon that's partially plus charged. So carbonyls are polar functional groups. Aldehydes and ketones, they're polar. Let's also take a look at a little bit about the shape. So because we now have this double bond in place, like we've seen with other carbon compounds, like the carbon-carbon double bond, we could describe now the shape or the bond angles that would occur between the various groups. All of the bond angles about this carbon are going to be 120 degrees. So these are trigonal planar in structure, so they have bond angles of 120 degrees. And this will be the case for all of the various carbonyls, whether it's an aldehyde ketone, or as we'll see later in the course, there's going to be other derivatives of carbonyls. So because of the polarity of this carbonyl bond, this tends to impart some physical properties that we really need to talk a little bit more about. So under the subtitle Physical Properties, let's talk about the polarity of aldehydes and ketones. So in general, if you have any sort of functional group that's got an asymmetric distribution of electrons, you can say that that's a somewhat polar molecule. And as we'll see through the course, there's a whole variety of functional groups that tend to lend more polarity versus not. But if I were to examine the boiling point or melting point of aldehydes and ketones. They tend to fall between alkanes and alcohols. So for example, if I were to list out butane, okay, which has that structure, butanal, which has this structure. One thing, make sure you're not pronouncing butanal in a phonetic way. This is not pronounced but-anal, but it's pronounced butanal. It's kind of a funny named compound, but that's the way it goes. And then lastly, butanol. Okay, so notice the structure of these is all fairly similar, but if I were to examine the boiling points of these, it turns out that butane boils at a quite low temperature. So if I looked at boiling points in degrees centigrade, erase that. Butane boils at about -1 degree centigrade. So at room temperature, it's a gas. Butanal, it boils a little bit higher, 49 degrees centigrade. But butanol, which has an alcohol group, boils at approximately 120 degrees. So because of the polarity of this carbonyl, the boiling point in this case has been elevated relative to butane. So why exactly is that? Well, if I looked at a simple compound that had a carbonyl, and I just drew two of them sort of stacked next to each other. In this case, this is the compound called acetone. But if I now drew the polarity of these, this is delta plus, this is delta minus, this is delta plus, and this is delta minus. Notice now if I put two of these molecules together, orienting delta plus and a delta minus next to each other, there is a slight attractive force. So this slight attractive force is what accounts for the slightly higher boiling points and or melting points of the carbonyls. They can, when they're in solution or in a solid, they can orient to have this weak attractive force. This force is definitely not equivalent to what could occur with, say, alcohols. Alcohols have the ability to hydrogen bond. I'll show you a little bit more about hydrogen bonding in the next section when we talk about solubility. So another physical property that's affected by the polarity of aldehydes and ketones is the solubility. When we talk about solubility, what we're really talking about is the ability or inability of a molecule to dissolve in water. So a compound that has a carbonyl in it, if I were to draw this out showing the lone pair of electrons on the oxygen, this has the capability of forming hydrogen bonds to water. And if you notice, there actually are two possible hydrogen bonds, one here and one here, coming off of the two lone pair of electrons to two separate water molecules. Notice, however, that a carbonyl can only act as a hydrogen bond acceptor. So it's accepting the hydrogen bond from water. Okay, because there's no presence of an OH group on the actual carbonyl, they cannot function as a hydrogen bond donor. So the ability of these lone pairs to now form hydrogen bonds with water help to increase the solubility of these when they're dissolved in water. So just as, to kind of illustrate this, if I looked at some very short chain carbonyls, so this compound is called acetaldehyde, and this compound is called acetone. These are two carbonyls that have just either 2 or 3 carbons in them. If I looked at percent solubility in water, these two have approximately 100% solubility. Okay, so in essence, I can mix equal volumes of these into an equal volume of water. But as we start to increase the carbon chain of carbonyls, the solubility starts to go down. So if I now looked at, say, 2-butanone, where I now have 4 carbons, this goes down to about 20%. And something like, say, cyclopentanone, it's now down at like 1% solubility. So as we increase the number of carbons this is a general rule on any functional group, generally the solubility does go down. But low molecular weight or small carbon number aldehydes and ketones tend to be fairly soluble. Once you get up above 3 or 4 carbons, though, the solubility of these tends to drop off significantly. So I hope that helps with sort of the structure and physical properties of aldehydes and ketones.